All right, guys, happy Friday. What we're going to do is go over your chemistry of the week 3 first. So if you want to pause the video and get that, we'll get started reviewing your chemistry of the week. All right, so here we have an exothermic reaction, and we're asked to figure out what happens to the reaction quotient and the position of equilibrium if the temperature is raised. So since this is an exothermic reaction, we need to figure out what happens when the temperature is raised. So if we increase the temperature, the reaction responds by trying to balance that change. So it decreases in temperature, which is not what exothermic reactions do. Exothermic reactions get hot, not cold. So because this is doing the opposite, decreasing in temperature when it should be increasing in temperature, that means that the reaction is going backwards. So it's going to shift to the left. So equilibrium will shift to the left. That's how we can get rid of A and C. Now we just need to figure out the relationship between Q and K. So K is whatever value it's going to be. But if we change the reaction conditions, Q is the one that's going to change. So if Kc is in the middle, then since we're shifting towards the left, that means Q must be greater than Kc. Question number 2, we have a weak acid and a strong acid that is titrated with a strong base. So we know the initial pH will not be the same, because the weak acid will be higher in pH than the strong acid. The initial electrical conductivity will not be the same either, because the strong acid is a better conductor. You would think it would be B, but anytime you have an acid and a base react, whether they're strong or weak, the same heat will be evolved in the neutralization process, because it's it all depends on the number, like the concentration, and the concentration is the same. So C is your answer, the volume needed to complete neutralization. You will not need as much to neutralize a weak acid as you will a strong base, or a strong acid, my bad. All right, question number 3. That one should have been an easy question. Your answer is B. Sublimation is when it goes from a solid to a gas, like when dry ice changes directly from dry ice to gaseous carbon dioxide. All right, question number 4, we're looking for the weakest conjugate base. So it means that we're forming from a strong acid. So we just need to look and figure out which one is our strong acid, which is A. Okay, so I want to go ahead and apologize for question number 5, because if you notice, all the questions are completely out of order. So I don't know what happened or why it happened this way. So I'm sure you got lost a couple of times. So what I'm going to do in reviewing this is I'm going to go in alphabetical order of questions, not in the order in which they appear, because it makes a lot more sense when you do it that way. All right, so for the first one, we're asked to find the balanced equation for the reaction that occurs. So in our reaction, we have magnesium that reacts with oxygen to form magnesium oxide. So that is what you're going to write here. You need to make sure your states of matter are present and that it is in fact balanced. So that's 1A. So now we need to find A2 over here. So now it says state the block of the periodic table in which magnesium is located. That was a gimme question. The S block. For number 3 down here, identify the metal in the same period that does not form a basic oxide. That would be aluminum. It forms an amphoteric species, which is neither acid nor base. So now we can find 1B here. calculate the amount of magnesium used. So if you look back at your data in the problem, we have the mass of the crucible and the lid here, mass of lid, crucible, and magnesium before heating. So you just subtract those two and you get 6.354 grams. Use the molar mass of magnesium to convert it to moles. So there we are right there. All right, now we need to find B2, which is here. Determine the percent uncertainty of the mass of the product after heating. So once again, we need to use our data from the problem here. So here's our product, crucible and lid. So we need to subtract this value from the mass of the crucible and the lid, which is how we get 9.569 grams. Then to figure out the percent uncertainty, I need to figure out the total uncertainty of this value. So this value has an uncertainty here. This value has an uncertainty here. So since I subtracted, I add my uncertainties together and I get 0.002. Now to find the percent uncertainty, I take my uncertainty divided by my measured value multiplied by 100, and that is my percent uncertainty. 1 sig fig. 1 sig fig. For B3, we're right here. We're asked to find the percent yield of magnesium oxide in the crucible. So we first need to figure out the amount of magnesium oxide we form. So we figured out how much we actually formed. Now we need to figure out theoretically how much we should have formed. So taking your value that you got from BI here, this is the number of moles of magnesium. Use the mole ratio in your balanced equation in part A to see that it's a 1-to-1 mole ratio. So this is the number of moles of magnesium oxide. Convert it from moles to grams, molar mass of magnesium oxide. And here's your theoretical value that you should have made of magnesium oxide. So to figure out percent yield, you take your actual amount that you formed, which you figured out from the question above, divide it by your theoretical mass times 100, and we get 91.1% yield, which is pretty good. All right, so now we're on to C1 over here. So once again, I don't know why I skipped all over. It says evaluate this rather than the loss of the product that could explain it. So I don't really know what this means, but what it's trying to get you to essentially determine is, if you remember from back when you started the problem, this is what was occurring in your crucible, but there's also this that's also reacting with the magnesium, the nitrogen in the air. So it's asking you to compare, you know, why your yield is so low. Could it be, in fact, that they reacted with some of the nitrogen? So yes would be your answer, because we should have formed 10.5 grams of magnesium. If we had magnesium reacting with nitrogen, the amount we would have made was 8.76. So if you look at the value that you actually made here, this is the reaction that occurred, this one, because we made a little bit less. But if this was the reaction that took place, was the predominant reaction, then our yield would have been closer to this value, but it wasn't. It was closer to this one. Okay, so then C2 says explain, other than losing the product to the crucible or reacting with nitrogen, why the yield was lower. And it could have been because we had an incomplete reaction. And then jumping back up to D1, this is just a balancing equation here. And skip them back. D2, determine the oxidation states. So magnesium is +2. There's 3 of them, so that's a total of +6. There's 2 nitrogens here. So take your +6 divided by 2. Nitrogen in this case must be -3. Here, hydrogen is +1, and there's 3 of them. So 1 nitrogen must be -3. So then D3 says deduce whether it's an acid-base reaction. So once again, going back and looking at your chemical equation, we see that we have water here is forming a hydroxide ion. So that means, yes, this is an acid-base reaction occurring. Is it a redox reaction though? Well, you'd have to look at the change in oxidation states between nitrogen and magnesium nitride and ammonia, and there's no change in oxidation states, so it is not an oxidation reduction reaction. So then coming up here to E, state the number of subatomic particles in this ion. That would be nitride, so that's 7 protons, 7 neutrons, and 10 electrons. E2, these are isotopes of each other. E3, talking about the difference between magnesium ion and nitride ion. So the nitride ion has fewer number of protons, so there's not as strong of a pull. There are also more electrons in its electron cloud, which causes even more repulsion, so that increases your radius. A, B, C, D, E, F. Here's F here, suggests 2 reasons why atoms are no longer indivisible units of matter. They're made up of subatomic particles, that's 1, and atoms can gain or lose electrons. G. Now we're on to G, which is to state the types of bondings in magnesium oxygen and magnesium oxide. On the back here. So with magnesium, that would be only metallic bonds because magnesium is metal. So that's a sea of electrons and a lattice of positively charged cations. Oxygen only has covalent bonds, and those electrons are being shared. For magnesium oxide, that's ionic bonding, and the electrons are being transferred from the magnesium to the oxygen. That's it. Yep. So once again, I'm really sorry that that chemistry of the week was all over the place, but hopefully you didn't struggle with it too much. So at this point, please make sure that the sub gives you the chemistry of the week 4, and please turn this in to the bed. All right, so let's get out your topic 9.2 notes. You're going to need that, your calculator, and your data booklet. So go ahead and pause the video while you gather all those things. All right, so today we're going to wrap up topic 9.1. So make sure the sub has given you the 9.2 PowerPoint notes and curriculum notes by the time you finish watching this. Yesterday we talked about the iodine and thiosulfate titration, and today we're going to talk about the final titration called the Winkler method. So just as a recap, the first redox titration we looked at was reacting iron with permanganate. So that is a 5-to-1 mole ratio between the iron and the manganate ion. Yesterday we talked about the iodine thiosulfate reaction, which is a 2-step titration. Even though it's 2 steps, the 1 mole ratio you need to remember is 2 moles of thiosulfate to every 1 mole of your oxidizing agent. Today, the titration reaction we're going to talk about is a whopping 3 steps. So even though it's a 3-step titration, the 1 mole ratio you need to focus on is the ratio of oxygen to thiosulfate, which is a 1 to 4 mole ratio. So before we get further down that road, let's talk about what the Winkler method is. So the Winkler method is a method to determine the amount of dissolved oxygen content in the water. So this is insanely helpful for environmental concerns. And basically it's measuring the level of pollution in the water. Because if the water is really polluted, then it has a very low amount of dissolved oxygen in there, which is a concern for the marine life that exists in that body of water. So the biological oxygen demand, or the BOD, measures the amount of pollution present. So a high BOD means that, once again, like I said, it's a very polluted area of water and that the level of dissolved oxygen is really low. So like with the previous titration, this titration takes place in a series of 3 steps. So what you do is you take your water. So in step 1, you take your water, you take your water, you dissolve the manganese ion in it. The ratio of oxygen to the product is a 1 to 2 ratio. That product, so once you titrate your manganese into your flask, your product, the manganese oxide, is then poured in the burette and titrated again with an acidic solution of iodide ions. And the product, iodine, is then titrated a 3rd time with sodium thiosulfate. That then you can use the relationship between iodine, thiosulfate, iodine, magnesium, manganese oxide to oxygen ratios. Like I said, it gets kind of complicated and confusing. You don't have to memorize any of these steps or anything, but the thing you must know is this right here. The ratio of oxygen to thiosulfate is a 1 to 4 ratio. So that's the main piece. So let's see this in a practice problem. So go to your next slide here and we'll look at a practice problem and you'll see what I mean. It's not really that complicated. It's happening in a series of 3 steps instead of 2 steps or 1 step. Still just 1 mole ratio you need to remember though. Right. Okay, here's your problem. Pause the video if you need time to write it down. We have 500 centimeters cubed of water collected and tested for dissolved oxygen. So that's pretty common, like going to a pond and collecting a sample of water. So you test it by adding the manganese sulfate in a basic solution, followed by adding acidified potassium iodide. 12.5 centimeters cubed of 0.05 mole per decimeter cubed of sodium thiosulfate was required to react with the iodine produced. We're to determine the concentration of dissolved oxygen of the water in grams per decimeter cubed. So this is when you know you need to use the Winkler method if it's asking you anything about dissolved oxygen content. So just like with any other titration problem, you start with the amounts of information you know the most about. So I have a volume of water, but that's all I know of water. I have a volume and a concentration of sodium thiosulfate. So I know both of those things, so that's where I'm going to start. Take your concentration of sodium thiosulfate. And just like yesterday and the day before, we need to get rid of decimeters cubed and only have our moles present. So multiply by decimeters cubed, divide by centimeters cubed, and then multiply by the volume in centimeters cubed. So now we're left with just our moles. So then take your calculator. And that's your sodium thiosulfate. Okay. So now all this other stuff seems really scary because a lot of stuff's reacting with a lot of things. And remember, that's because it's a 3-step titration problem. But all the steps, it doesn't matter because the only thing you need to remember is this mole ratio. So it's 1 oxygen for every 4 thiosulfates. So here, now we know our moles of thiosulfate. From the 3 steps, we know that it's 4 moles of thiosulfate for every 1 mole of oxygen. Okay. So now we know our moles of oxygen. We want to figure out the oxygen content of water in grams per decimeter cubed. So we have our moles. So we need to take our moles and convert it into grams. So oxygen's molar mass, 16 ounces. So there's 2 oxygens, so that's 32 grams. 0.005 grams oxygen. And so now we're in grams. We need to find decimeters cubed. So if you look back in your problem, we're given 500 centimeters cubed of water. We want decimeters cubed, so we need to divide by 1,000. So to get into grams per decimeter cubed, you just take your grams divided by the decimeters cubed you just found. 0.01 grams per decimeter cubed. Okay, so that's it. Like I said, seems scary at first, but it's literally the exact same thing that we've been doing for the last 3 days. The only difference, your mole ratio here is 1 to 4. And then for the iodine thiosulfate reaction, the mole ratio is 2 moles of thiosulfate to 1 mole of the oxidizing agent. And then for the one step, it's 5 to 1. So if you want to make flashcards of just the 3 mole ratios, that would be insanely helpful. You just need to know those things. Okay. So make sure that the sub has given you the chemistry of the week 4, that you have your 9.2 notes and your curriculum notes. And for the rest of class, you can either work on your lab report, which is due on Monday, or your chemistry of the week, or your 9.2 notes. Okay. I will see you Monday, my children. Can't wait.